Hello friends, welcome back to the Dr. Tristos channel. I'm Dr. Tristos. You know, you know who is here again. That's right, the boss. It was like when you started this demo program, you promised us that it would do something useful. And so far it hasn't done anything useful. So I found out that occasionally they need the square root of an integer between 1 and 255, and I thought this would be my opportunity to provide my manager with a program that will calculate the square roots of those integers. He can run it in the Zilog development system. He doesn't need any hardware. It's completely free. All he needs is the ZDS system on his desktop, and he'll be able to turn around and run this program and turn around and find out what those square roots are. They're going to be greatly rounded, since we only have an 8-bit number to calculate with, but nonetheless we can do it. And here again, it's a good example of subroutines and how we can use subroutines and macros to our advantage, and also includes, so that we don't have to have everything in one file, but that we can break things up in multiple files and modules, and then assemble those modules together using our include statements. And this also is very convenient if we build macros or subroutines to have them in files, and they can then be included in other programs. We don't have to retype everything or copy and paste it in. We just include the file. So with the emulator that runs in the ZDS, I'm still praying somebody will build me a high quality EZ80 emulator that would allow us to input keystrokes and output characters on the UART. But since we have this development system, it simulates a basic UART for output only. We decided this is what we'll use. So again, let's look at our program. We've pretty well covered everything that we have going on here. Example demo is orged at 3000 hex, which is a starting place in Tristos for most apps to start at. We have a data area. We bypass that. We jump to begin app. We bypass the data area. And since we're using a subroutine and stacks, etc., first thing we do is initialize a stack. I'm pointing to the last byte in the 64K address space, FFFF, hexadecimal. And we use that first macro we developed, pump, and we send out my screen, which we have decided is this screen here. And it's going to pump all this out the UART down to the end of text .ASCII character. Okay. So back in the old days when we had punch cards and things, you didn't interact with the computer like we do today, but rather if you wanted problems solved, you've done that one of two ways. Either you used equates to give the program the parameters you wanted solved, or load it into memory, or you would put the data on punch cards And when your program's running, you would have things in the correct sequence instead of prompting you on your screen to enter the next file name or, enter the value you want square root solved for. It would read the next card, or if you had it in memory by doing, for instance, you're putting things in storage with defined bytes. It's going to read it from memory. Your program was designed that way because nobody was interacting with the computers back then except really the operators. But that's a good lesson in how we use this emulator here because we can't type anything in. So anything we want solved, we need to put that data in the program, let it solve it, and we can output to the UART so we can see the answer on the screen. So we've decided that we want to see the way this program is going to work is we're going to give it a number, and it will take from that number down to 1, counting backwards. It'll give us the square root for each number, integer. So we decided that since our maximum number can be 255 in the accumulator, we'll just start our counter at 255. So here I've equated square to 255. And down here, load B, B is receiving, I'm going to say, get num to solve square root 4. So now we have that in the B register. We're going to save that here, and we're going to start a loop, because remember we're going to go 255, 254, 53, 52, all the way down to 1. So we're going to set up a loop here called my loop. Okay. Now the first thing we need to do is we need to tell the people what we're solving a square root for. So here we need to move the data around the registers a little bit. I need to get that number in the L register, and we do that here. We put a 0 in the H register, so now the H and L register has the value we're trying to solve in 16 bits, although we're just using the lower 8 bits of the register, but it does have it in 16 bits. And the reason for that is we're going to convert a 16-bit number to decimal. So the D and E register here is going to point to the square root string plus 15. So let's look at square root string. Right here it is. Okay, so the first S, that's square root. Square root plus 0. Okay, and we said square root plus 15. So that's plus 0, points to the first character right of my cursor. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The first character right of my cursor, these X's, is where this pointer that we load into DE now points to this first X. We're going to convert a 16-bit number in the H and L register pair binary to decimal. So it's now going to convert this to decimal. The maximum size number this could be would be 65535, 65,535. So we need 5 digits to hold that. We do that, and we're going to start off at 255. So what it's going to output is 00255. It's going to have leading zeros. So we then call a trim zeros subroutine called trim zeros. And you don't see that here on the screen, but it's part of the subroutine file. Now those samples, like trim zero, is here in the subroutines, and we include the subroutine file down here at the bottom. We don't want it at the top because we don't want the code before the program. Subroutines would have code. Normally we would put these at the bottom. As long as you make sure that you know where you put it and that you're not going to start executing it unwantedly, then I guess you could put it anywhere you wanted. So we have them at the bottom. I can tell you that call trim zero, the trim is going to start where their H&L register pair points, starting at the beginning of our number we just put in here. So I just said this is going to have 00255 will be what it has in the first time through the loop. Trim 0 is going to come in and it's going to take off the leading zeros. So this says 00255. It's going to take off the first 0 and replace it with a null character. It's going to take off the next. It says a 0. It'll replace it with a null character. Then it runs across, it hits the 2. The first non-zero digit that it hits, it's going to stop. So we can take a look at that in my subroutines. A little routine I wrote here. Trim zeros right here. So when we enter this, H&L already points to the string. And the first thing we do is load the accumulator with an ASCII 0. And that's important. It's an ASCII 0. Okay. We compare it to where the H&L register points. If it is not a 0 there, then we have ran across the first non-zero character and we can return. It's non-zero, we can return. Now, if it is a 0, we continue on and we load into memory where H&L is still pointing an ASCII null, N-U-L-L. So it's a binary 0 it's going to put in there. We're going to increment the H&L, point to the next character, and then go back around our loop to trim zeros. It's going to loop around in this routine until it runs across the first non-zero character. Suppose if you pointed it to 60 kilobytes of ASCII character 0, it would sit there and go through all of them and replace them with binary 0. This is very important because when it prints out, you don't want 000255 to print out. You just want 255. Okay? We don't want spaces in front of that 255. That's why we use a null, a binary 0. If we did want spaces, we could replace this right here with an SP.ASCII, a space 32. Then you'd have a space where the leading zeros were. Or maybe you want some other type of character. Maybe you want the English pound sign or something, just to show that there is no leading characters. You know, and things that's really super important. Sometimes you do that, and that way people can be certain, well, the printer didn't just drop a number here. This column was intentionally left blank because the 0, you know, the number starts with. So the leading pound signs says, no, the printer didn't drop the digits off or something didn't happen. There wasn't a problem with the ribbon in the printer. It's just that there is no digits there. So it depends on your application, what you're trying to accomplish. So after we trim the zeros off, we then recover our registers here. We get the B and C register back. Remember, B contains, let's see, B contains our counter. So the square root program calculates what is the square root of what's in the accumulator, the A register. So we load the accumulator from our B register. Remember, B has what we're solving for. We load that into the accumulator and we call our square root program. I'm not a mathematician. I guess somewhere long ago I got this routine from someone somewhere, and like a good programmer, I copied it. I'm not a mathematician. It's pretty amazing to me that for an 8-bit number, that's all it is to solve the square root. Any number that's a power of 2, I guess they can do that relatively easy here with a short loop. Again, if I had to solve that problem, it'd probably take a while. But I did find sometime back the code for solving it for an 8-bit. I saved it, and we're using it here. I would give credit to if I knew where it came from, but I don't know where it came from. So we call the square root, and right here, where are we? Oh, right here. So here we call and solve for the square root. When we return, I have to get my bearings here just a minute. We have to then convert the answer to a decimal number so you can read it. So the answer is in the B register. We now move that over to the H and L. The H has 0, the L has the 8-bit. That makes we've converted it to a 16-bit number that's contained in the H and L register pair. The D and E is going to point to square root, which is right here. Square root, I've done another example of equate. It's the program counter minus 6. Right now, the program, the pointer, it's not really a program counter. It is during the assembly, I guess you could say. It's pointing right here to ETX. So if we go 6, we're going to back up. It points to this last X. That's 1, 2, 3, 4, 5. I'm sorry. We have a carriage return at the end of this line. So if we're going to back up 6. There's 1, 2, 3, 4, 5, and 6. So now we can see that the D and E register pair is pointing to that group of 5 X's at the end of the sentence. We're going to call our convert 16 again, binary to decimal. Remember, we said it's going to convert the 16-bit number, which is really we're just using 8 bits. It's going to convert it to decimal and write that decimal number in ASCII right here, because this is where our D and E is pointing, right? We've set it up that D and E is pointing to this spot. So it's going to write it right here, leading zeros and all. Again, we'll point the H and L register pair to square root, which is equated minus 6, means it's right here. X's. We're going to call the trim zeros, which means it'll take off the leading zeros and leave us with just the answer. And then we're going to output this answer right here using our pump macro. We'll go ahead and send the output to our UART. At this point, we'll recover our counter next. After we send the output, we'll recover our counter. We'll decrement the B register, and if it's not 0, we're going to go back around to my loop. First thing we do is save that counter again. So it's going to keep looping until it goes to 0, and then the CPU will halt. So let's compile, assemble this, and then run it, and see how it looks for us. Hopefully the boss will be happy. We're doing a useful job now. We're calculating the square root of something. How could he not be happy, you know? Let's see. Assemble it. Oh, we got 2 warnings. What did I do? Syntax error. Did I leave something in the... Oh, yeah, right here. That's what happens when you're editing and fooling around. You can accidentally take characters out of the... I will assemble again. We're going to run that. And over here on the right, we have the UART output. And that's always something handy to have. So, you know, I had to try it 2 or 3 times. It's something I say about sometimes the quirk of this development system. I didn't change anything, but I had to try 2 or 3 times to run this before I got the output on the UART. So here we can see that the program has done what we told it. First, it printed hello world here on the right, and thank you message. Notice there's 3 carriage returns. See how we have our blank lines there? Okay, first carriage return, second and third. Then we have a square root of, and you notice the x's are gone, and we've replaced that with the numbers. Starting off at 255 and counting backwards. The square root of 255 is 15. Now, you know, we got an 8-bit number, so we're definitely going to have some rounding problems there. Let's see how close it is. 255. I'm sorry. 15 times 250. What am I doing? 15 times 15 is 225. So it was within 30 here. So when we get down to 225, here's the first time that it's an accurate square root. The square root of 225 is 15. So, as you can see, keeps going right on down. Square root of 9 is 3. Square root of 25, I'm doing the easy ones, it's 25. Okay. Let's see, what is square root of 120 is 11, I think, isn't it? Maybe not. 122 or something like that. 121 is the square root of 11. So all the rest of them are numbers that's been rounded. So here we see that even with the emulator running and just emulating a UART for output, we can do some useful programs. Not sure how useful it is, but it certainly is useful as a teaching tool and learning how to use the assembler and learning the instructions, especially if you're learning the new 24-bit instructions, because you can try the instruction here in the code, stop it, come over here, look at the registers, look at the look at the output and determine. As we go up here in view, debug windows, tell it we want to see the registers. We have to stop the program so we can see the registers. Here's our registers. it's very powerful. We have a lot of things we can view here, a lot of different debugs that can get in and see the memory we're working with, and a disassembler. It's really powerful. So I encourage you to, maybe you want to download this demo and go in and play with the code and make your own. I'm going to put a link to my download page in the notes of this video, and the comment section I'll put the notes or the link, and maybe you'd like to download it and get your own ZDS and learn how to do this. And I would certainly like to hear from you if you do, and if you have any questions or comments, please post them in the comments, and we'll keep on. We're going to do some more videos. I'm going to do a video on advanced macros, because you'll notice here at the bottom I have a macro, and it's going to be in the sample files, but I put this macro in and then treated it as a subroutine and called it. And there's reasons that you may want to do this, and you can use the macro feature to create powerful subroutines that can be used in different programs simply by on your input to the macro. You can give parameters. I don't have any on this one. It's just a simple macro with no input parameters, but we could have input parameters out here on the right that would help configure this, and it's basically being treated as a subroutine. If you notice here, this label, I'm calling it up here. So here's a macro that's been loaded in memory as a subroutine. And because, there's times when a macro is appropriate and there's times when a subroutine is appropriate. And sometimes you can combine and kind of get the best of both worlds. All right, so I hope to see you back here again. I'm going to upload this, and if there's anything I can help you with, please let me know. Thank you.